Hello, I am Tarandu Kalwarachi. I am presenting waveSense, a novel low-power voxel-tracking technique. The introduction of virtual reality devices requires interaction methods that go beyond traditional pointing technologies such as buttons and touch screens. Therefore, modern virtual reality headsets have advanced gesture tracking systems that precisely track the hand gestures. However, these techniques require specific hardware that has a higher computational capacity to run computer vision algorithms that consumes a lot of power. Therefore, our main goal with waveSense is to develop a low power and sparse hand tracking system with low processing overhead for resource limited devices. Existing work has explored ways to track human hand to detect gestures and for other interactions using different techniques. OmniTouch uses a projector and a camera to project on the hand and to detect hand movements using computer vision algorithms. MIME uses a camera and an illuminator to detect hand gestures using computer vision. Imaginary interfaces also uses a camera to track the hand. In contrast, SightSight uses an array of IR sensors to track finger gestures. Most of these techniques use a camera as the main sensor, which consumes a lot of power, and the IR based solutions also use a higher number of emitters and receivers, consuming a considerable amount of power. We introduce selective volumetric illumination, a novel illumination technique that uses variable emission powers and sensors in binary mode to achieve low power hand tracking with small data throughput. This results in an extended sensing range, improved immunity to background noise, and lower energy consumption compared to other alternatives. We developed wavesense based on selective volumetric illumination. We leveraged the resolution versus power trade-off to reduce the power by optimizing the system to run in the optimal resolution. WaveSense is built upon our prior work CSense, which also is an IR-based finger gesture recognition system. In contrast, WaveSense can detect hand gestures at a lower power level within an extended sensing range. In WaveSense, IR emitters work in a binary mode compared to the analog mode in ZSense. We tried using 3 different sensor positions at 8 different power levels, keeping the emitter at a constant location to determine the position of the hand. As you can see from diagrams A, B, and C, we can leverage these illumination patterns to track the position of the hand to train a machine learning algorithm to classify gestures. We decided to go with 3 power levels, which were enough to detect with sufficient accuracy. The working principle of wavesense is shown in the diagram. IR emitters work in 2 states, which are on and off at 3 different power levels. The digital signal generated by the IR emitter is modulated using a 57 kHz signal so that unnecessary IR emissions do not interfere with our system. That's adding improved noise immunity. On the right side, there are the PCBs we developed for our prototype. We ran a study to understand the capabilities of wavesense. The graphs show the predicted and the real position of the hand. This performance was sufficient to detect and differentiate hand gestures for our envisioned applications. The first application that we developed was an image gallery operated using hand gestures. a person can push or pull or swipe to zoom in and zoom out images and browse through the gallery. The second application we tried was a game that can be operated using 4 hand gestures. Those hand gestures were pushing the hand at 4 different angles to destroy the enemy tanks coming towards the gamer. In summary, we contributed with selective volumetric illumination that results in lower power consumption, extended sensing range, and improved noise immunity in IR-based gesture recognition systems for resource-limited wearable devices such as VR headsets. Thank you.